Good morning, everyone. Welcome to the fourth and final webinar in the Bitumen Beyond Combustion series. I'm Carrie Romanitz, the program coordinator at COSIA, and I'll be hosting today's event. You can catch up on any of the previous webinars at vimeo.com/COSIA or also on stantec.com. This series was designed to provide an overview of Alberta Innovate's exciting initiative to advance the development of non-combustion products from Alberta bitumen. In the recent Phase 2 report, Stantec Consulting was commissioned to expand on the BBC concept and examine additional business opportunities for products such as carbon fibers, asphalts, and polymers, the latter of which we'll be discussing today. So at this time, I'd like to introduce our presenters. First, we have Paulo Bombin, Alberta Innovate's Senior Manager of Clean Technology Development and Program Co-Lead. We also have Axel Meisen, Senior Advisor and Program Co-Lead with Alberta Innovates. From Stantec, we have Nathan Ashcroft, Stantec Team Lead, and Ken Harding, Senior Advisor of Energy and Chemicals. So today, this is our agenda. We're looking at about 40 minutes for the program, followed by 15 minutes for Q&A. If you have any questions throughout the presentation, just type them in the Skype message box, and we'll get to them at the end of the presentation. So with that, I will turn it over to Paulo.
Thank you, Carrie, and good morning to everyone, wherever you might be in the world listening in on the webinar. Before we begin talking about polymers and our discussion on that topic, I'd just like to discuss a little bit about the bitumen beyond combustion concept and share with you sort of a visioning of how you might interact with bitumen beyond combustion products in the future. For those of you who've been on previous webinars, you'll notice that this is familiar, but for those of you who are joining us for the first time today, this will provide you with some background on BBC products. So to share this, what I'd like you to imagine is that you're on a drive home from work, and your drive is about 10 minutes long. And in the first minute, on the right-hand side of your drive, you see a new condo project that's going up. And that condo project is built primarily of wood. But not just any wood. That wood is actually reinforced with carbon fibers. And those carbon fibers, the carbon in them originates from bitumen. Those carbon fibers are adding rigidity, strength, and durability to the wood, ensuring that this condo project will last for a long time. And so that's your first touch point with a BBC product. As you continue driving down the road, you notice that the road is actually in really good shape and hasn't been paved in quite a long time. And that's because the asphalt is made from components of bitumen. The asphalt is more durable, longer lasting, and less prone to rutting and cracking. So this is now your second touch point with a bitumen beyond combustion product on your drive home. As you continue about 5 minutes in, you see a wind farm and a bank of solar panels on your left-hand side. And along with those solar panels and wind turbines, there's a battery bank at the bottom. And the battery bank are vanadium flow cell batteries. And the vanadium that's critical to their operation is extracted from bitumen. And so that's your third touch point. As you finish your drive home, you're consuming your iced latte or tea through your straw. And the straw, being a polymer plastic, which we'll talk about in today's webinar, is made from constituents of bitumen. And so that's your fourth touch point on your 10-minute drive home. And so this illustration really is to share with you how you may interact with bitumen beyond combustion products in the future, how they will impact everyday life and enhance our everyday lives. I also want to point out that over the last few months with this webinar series, along with that, we've also generated a lot of interest in BBC in terms of the media, but also not only in Canada, but around the world. And so we've also been profiled in The Economist. And so this concept of a bitumen beyond combustion future with its products is gaining a lot of interest and traction amongst many people and stakeholders. And so that's really a quick background and snapshot on BBC. I'd now like to transition back to the topic of today's webinar, which is polymers. And as we go forward today, there's a few key questions we'd like you to consider, and that we'll also provide some commentary on. And the first one is, if we are going to make polymers from bitumen, what polymers should we make? There's a wide range of polymers that are manufactured globally right now, and so which ones are best to target from bitumen? And once we've identified what polymers we'd like to make, how do we actually make them from bitumen? And that's another key question that we'll explore through today's discussion on polymers. And so with that, I'd like to pass the mic over to Ken from Stantec, who will take us through some polymer essentials.
Thank you, Paolo. Good morning, all. In the next couple of slides, we're going to touch on polymer essentials. What are polymers? Maybe just as a start to this slide, just to highlight to the audience that the focus is on solid polymers, and that the terminology polymer and composites, sorry, not composites, but rather plastic, is used interchangeably. Very often the word polymer is used from a production perspective, and the word plastic is used from an end user perspective. As an example, where's my plastic bag? Where are polymers? Where do we experience them daily? Well, in short, plastics and polymers, they are synthetic material made from a single or combination of polymers with various additives such as pigments, UV stabilizers, and such like. We find application in the consumer, industrial, and medical applications, adhesives, bubble gum, carpeting, clothing, cosmetics, drill muds, flooring, furniture, hygiene products, specifically in packaging and beverage bottles and such like, all the way into water treatment. And really, polymers, be it a solid or a gel of some form, is an essential part of everyday life. What are polymers made of? Polymers are made of monomers, and the word monomer refers to one or a single unit. An example is shown on the right-hand side for styrene, and styrene is a monomer, is a liquid, but once polymerized, that is linked up with its fellow constituents into a long chain to create a polymer chain, it becomes a solid product. And two examples on the upper right-hand corner is shown for polystyrene cups, and likewise in the construction industry. The exciting part about polymers is that the backbone, the chain length, can be varied depending on process conditions. You can have short, medium, long, and very long chains, and naturally these long chains dictate the application in which the polymer finds itself. Where do polymers come from? There are three basic types: natural, semi-synthetic, and synthetic. And quite naturally, semi-synthetic forms a link between natural polymers and synthetic polymers. Looking at some examples of natural polymers, the first one we look at is a polysaccharide. Examples of that are cellulose, glucose, chitin, cotton, keratin, and starch. And the purpose of a polysaccharide is either for energy storage or for structure. Another example of a natural polymer is natural rubber and polyisoprene. And typically this is where you encounter this on a daily basis is in your car tires. Historically, natural rubber was and still is extracted from the natural rubber plantations in the hot tropics. A third example is the polyaromatics from lignin. And the fourth is proteins, an example there being silk. The additional purpose of this slide is to illustrate that amongst all the natural polymers, there are varying structures between them all. And these structures dictate the final application in which the polymer is used. Moving on to semi-synthetics, the first example, and only example we look at, is cellulose acetate. The feed here for cellulose acetate is a purified natural cellulose, either from cotton linters or wood pulp, and is then acetylated. The acetylation gives the product a particular end property. Cellulose acetate has been used for cigarette filters, Lego bricks in 1949 to 63, and probably the major use that we recognize of cellulose acetate is in photographic film by Eastman Kodak. Synthetic polymers played a very small role in the world back in the 1950s. Only 1.5 million tons, 2 million tons of it was produced. A significant amount, yes, but still trivial compared to the 380 million tons that is produced today, or around 2015. A key enabler of this has been the rapid development in synthetic chemistry and material science. Early examples of synthetic polymers were that of Tupperware at DuPont and likewise Teflon in 1938. If we look across at the synthetic polymers are produced from monomers, and the monomers in turn are produced from petrochemical feeds and intermediates. As said earlier, an example of a monomer was styrene, and there are many, many other examples, such as the acrylates, acrylic acid, and so forth. Polymer development was since the 1950s and continues to be driven by the demand for improved product, be it strength, rigidity, flexibility, and so forth. A key advantage of these synthetic polymers is the range of monomers that are on offer to the synthetic formulating chemist and engineer, and this offers a great opportunity to formulate and develop new polymers using the principles of molecular design. Technology development in refining in the petrochemical sector has also contributed to the growth of the polymer industry. Likewise, geographic availability of natural polymers has meant, and the general growth in population has meant that synthetic polymers like polyisoprene have come to compete with natural rubber. Logically, politics, economics, and society have also contributed to polymer development since the 1950s. In closing on this slide, just to reflect back, the synthetic polymer industry produced around 2 million tons of polymers back in the 1950s. This has grown for the major group of polymers shown in the block on the right-hand side to 380 million tons per annum. This market will not disappear and is expected to grow significantly. The applications in which we find these polymers used are numerous. The first one is commodity plastics, and these are there for ease of use and convenience. And the two examples we have is polyethylene terephthalate, pop and beverage bottles, and likewise polystyrene for food packaging, coffee, and such. If we look at polymers with increased engineering and sophistication, with enhanced mechanical and thermal properties, we have PVC, polyvinyl chloride, used in the plumbing and piping sector, and then polycarbonate, used in the optical media industry. Still, again, there's another category, higher performance plastics with increased mechanical and thermal performance, such as polyurethane foams and SBR or styrene butadiene rubber, used in the tire industry and aircraft industry. A key principle to take away from this slide is that the products shown, they are not a single polymer. They're a combination of materials, which does include other polymers and materials like fillers, UV stabilizers, fibers, pigments, processing aids, and so forth. They are truly engineered composites that have and bring valuable contribution to everyday society. The advantages are many. The one detriment, however, is from a recycling perspective. This complexity of the composites does produce considerable challenges. The products are mostly inseparable, and if they are, and where they are recycled, they typically find their ways into products of lower technical quality and quality requirements. An example of this would be plastic extruded wood. With that in mind, I'd like to hand over to Nathan Ashcroft that will take us through opportunities of polymers. Thank you.
Thank you very much, Ken. So let's talk about the opportunity here. Plastics, polymers are parts of everyday life. So if we're sitting in an office right now, look at our computer screens, our TV screens, our desktops, parts of our chairs, in fact the carpets, we're surrounded by polymers in every part of our lives, and that's not changing. The global plastic market, polymer market, currently is sitting around 650 billion a year. It is a huge market, and there's elements that are missing from that. By our projection, using the growth rate of close to 4%, this is expected to grow to a $1 trillion market by 2030. This is a huge market, and we have the graph down below. What are the drivers for this? Well, as we have increasing population and urbanization and middle class and people coming online and wanting more things in the developing world, as well as ourselves who continue here in Canada wanting more stuff, as we call it. That stuff is usually plastic or polymers. It includes that. So this isn't changing. However, there are some things that are changing with respect to the environmental aspects and biopolymers, and I'll talk about that shortly. The different groups of polymers, if you look on the right-hand side of the slide, we've picked the top 8 groupings of polymers from polypropylene down to polystyrene, and that there's approximately 407 megatons per year of those polymers. These are approximate numbers that line up with the graph. And what we did, just for reference, we did some rough approximation that if we were to produce all those polymers from bitumen, how much bitumen per day would that be? And I will emphasize this as a rough calculation. And it was around about 5.5 million barrels a day of bitumen, which is close to twice the amount that we currently produce. Life's not quite as simple as that, but just gives you a context of how much polymers there are around the world and its relation back to a source for making them. Some concerns with existing polymers. Let's talk about that. So, as we've been seeing of recent times, there's been a lot more government legislation, UN, around in Canada we've heard a lot about plastic waste. With this amount of polymers and an explosion and growth, as Ken alluded to earlier, we have some challenges. So we decided to pick up on a couple of different examples here to maybe illustrate some of these challenges. Beverage bottles, polyethylene terephthalate, PET, as it's shortly known. It's used widely. Why is it used widely? It's flexible, strong, light, non-toxic, 100% recyclable, but importantly, not biodegradable. And as this gets mixed with different forms of plastics, it's very difficult to recycle this. Look at the volume number here. Approximate numbers, 50 billion plastic water bottles from PET made in the US last year. 50 billion, that's a huge number. On average, it works out to be approximately 150 bottles per person. So you could do the calculation what that would be for Canada and around the world. We're talking about a huge challenge that's emerging in this world that we have that's surrounded by polymers. Waste globally, over 6 million tons of plastic waste that we're producing. That was of 2015. Approximately, and it is changing slowly, is 80% of that number is going to a landfill. So our world that wants all these great new products, we also have challenges that we need to address. Just another example here, something that we perhaps don't think about as much as plastic bottles, is carpets. We have them in office space, at home, all sorts of different places. And these are very complicated polymers. They have all sorts of different aspects to them, adhesives, anti-statistics, pigments, UV stabilizers. These are all different forms of polymers, and it's not biodegradable. And there's some numbers there around the European Union and the United States. Again, huge quantities of complicated polymers that what are we going to do with it? Well, two choices at this moment in time, essentially. Let's go to a landfill or we incinerate it. So there's some real challenges here. Let's talk about why there are challenges with it. So these polymers, they have forms of degradation, but those forms of degradation are pretty limited. They're either mechanical or chemical. Mechanical, if it's in a sea or a river, it's the wave motion breaking these components down, which you can imagine is over a long period of time. Similarly, from a chemical perspective, a microbial breakdown, whether it be aerobic or anaerobic, whether it be from sunlight, UV, or whether it be through thermal cycling, very cold temperatures and very hot temperatures. This takes a long period of time. So why is that? So when we design our polymers for different uses, and you look on the right-hand side for our homes, our vehicles, some aircraft and everyday use, we don't design these polymers to degrade. I mean, if we had a function for the polymers that I've mentioned, and after a year or two they start to fade away, whether it be a bicycle or a car or a house, we wouldn't be happy. So they're not designed that way. So modern polymers, as Ken alluded to earlier, these are very different to natural polymers. These are synthetic. They're largely, due to reasons I'll explain shortly, biochemically inert, And the degradability of these is the function of the chemical composition. And down below we have two samples on polyethylene, a synthetic polymer, and cotton. Polyethylene, here you can see the carbon backbone. And it's very difficult to break down. It's somewhat biochemically inert, as opposed to the natural polymer, cotton here, that has a carbon-oxygen functionality that does break down. So there are real challenges with breaking down. Challenges also come with some opportunities. So just as a reminder, the polymer world globally, 654 million, growing to $1 trillion. Where are we at with biopolymers in the scheme of things, knowing that we have this challenge that we have to address? Biopolymer outlook is still pretty strong at 4%. But look at the numbers here. We have in 2016 approaching 7 million tons produced, 7 million tons of biopolymers as opposed to close to 400 million tons. This represents less than 1% today of the global polymer production. Even through the forecasts growing to 2021 through to 2030, this represents maximum of what we've seen is up to 5% of the total polymer market. So when we look at the opportunity around polymers, our world is surrounded by them. We need them. They're a part of our society. But the opportunity to make them in the future, new ways to do it, we really need to look at the bio aspect in more detail. But to talk about how we actually make polymers, I'm going to hand over to Axel, and we'll walk through the steps of what's involved there.
So thank you very much, Nathan, and I also welcome everybody to the webinar. In the next two slides, I would like to address the ways in which we are making synthetic polymers. Each one of these polymers has a complex and sophisticated production process. But instead of giving you a lot of details, let's just try and generalize and view the processes as black boxes. And it might be represented by means of this simple flow sheet, which is a schematic flow sheet. Imagine that we have a hydrocarbon feedstock of the kind that Ken already mentioned, and there may be some added feedstocks required, such as chlorine, if you want to make PVC. And we end up making a polymer, and was stated most of the synthetic polymers currently are neither biodegradable nor compostable. What's happening inside this black box, which is the process? Well, there's a series of reaction that takes place, typically at elevated temperatures and pressures, in the presence of catalysts, and these reactions proceed very quickly. Residence times are measured in the order of minutes in typical processing equipment. There are also numerous separations, and ultimately the polymer that you make has to be formed and shaped in a particular way, either granules or fibers, for example. Let's concentrate on the feedstock. All current synthetic polymer production processes call for very pure feedstocks. That's true for the hydrocarbon feedstocks as well as the other feedstocks that might be added. So if we think about bitumen as a feedstock, we're right away faced with the challenge that bitumen, which is a complex mixture of many hydrocarbons, that bitumen would have to undergo extensive conversion and separation, all of which bear a cost. And therefore bitumen as such is not an ideal feedstock for the kind of synthetic processes that we currently are operating to make our synthetic polymers. Let's compare and contrast that with the way natural polymers are being formed. And you might like to think about spider silk, or the silk that spiders produce. What does that look like? First of all, the polymer, of course, is biodegradable and compostable, so that is one way of distinguishing them from synthetic polymers. And the feed and the processes that occur inside the spider are generally low temperature, low pressure processes. They are enhanced by enzymes, but they're really slow processes, measured often in terms of days, certainly hours, but in many cases days and sometimes weeks in order to make the polymer. If you think about chitin, which forms the shell of insects. And then if you think about the feed is not a pure monomer, it's not a pure compound, but it's a mixed feed. Maybe other animals that the spider feeds on, vegetable matter that it produces. So that's really quite different from the way in which we currently make synthetic polymers. If you try and project that then into the uses of bitumen, if our processes, as yet undefined, can in fact accept a mixed feed, then that comes closer to what bitumen actually constitutes, and the conversion and separation wouldn't have to be as sharp as it would be if we needed a pure feed. So all of these processes can be combined into a generic flow sheet, which is shown on this slide, where if we want to make the polymer, we can make a decision on whether that polymer should be biodegradable or compostable. It may be, but it's not necessary. The processes that occur in order to make the polymer, if they're based on catalysts, they would typically run at elevated temperatures and pressures. But if they were using enzymes, then they would operate at lower temperatures, more ambient temperatures and pressures. And in terms of the feedstock could be mixed if we base it on enzymes, and therefore the pretreatment for bitumen, if we use bitumen as the primary and initial feedstock, would be less onerous. A point that I have not mentioned in conjunction with the other flow sheets, but I want to bring out here, is that all processes, whether they are natural or synthetic, require energy. And particularly the processes for the currently produced synthetic polymers require large quantities of energy. And we're very conscious of the fact that this energy has to be green energy, and preferably energy at a minimum level. So that's an overview of the process flow sheets. And I would like now to hand it back to Paolo, who will speak about the technical challenges of polymers.
Thank you, Axel. Nathan, Ken, and Axel have taken us through some of the backgrounds of polymers, and as well as the way that polymers are made. And Axel began to allude to the way polymers could be made from bitumen. And so Axel alluded to some points, number one being that bitumen is a mixture. I'd also like to point out that what bitumen does contain, that maybe some of the other synthetic polymers don't, as a feedstock, bitumen has other elements, such as oxygen, nitrogen present as well, as opposed to just carbon. And those oxygen and nitrogens are valuable, as Nathan pointed out, into leading to the biodegradability as well as the compostability. So that makes bitumen a very interesting feedstock from the perspective of potentially making polymers. But now what are those technical challenges, though, that we face to make this a reality? And so I'd like to take you through a few of them. There are certainly more that you might imagine, but I'll take you through three of them on this slide. So the first one is around the choice of polymers. So as is indicated by Ken earlier, polymers have are really designed for purpose. So they have different properties and characteristics that meet the expectations of the end user. Those might be performance related, cost related, built in with reuse and recyclability, environmental and social acceptance. So the first thing we really need to consider is what type of polymers do we want to make from bitumen? If we pursue a conventional synthetic polymeric route, some of those expectations on the previous line might be inherently challenged, such as those around reuse and recyclability, as well as environmental and social acceptance. However, if we consider some of the unconventional synthetic polymers or pathways, such as the natural pathways that Axel alluded to, where polymers are cross-linked, maybe protein-based, have irregular monomeric patterns or random monomeric patterns, we may see more promise in meeting all of those expectations listed on the line above. So really that first question is, what is the polymer that we choose to make? And very much in line with that, then once that decision has been made, what pathway do we take to making these polymers? And the flow sheets that Axel related to for conventional synthetic polymers are quite well established, and the production of polymers from bitumen could be integrated with traditional bitumen refining potentially quite easily. Whereas for the unconventional synthetic pathways, many of those are largely undeveloped. And so it will take a lot of ingenuity and work from engineers, scientists, those on the line today, the broader community, to make that a reality. However, to make those unconventional synthetic polymers, that's the path we have to take. So that's really the second big challenge that we face when considering how to make polymers from bitumen. And the final one that I want to point out today is, Axel alluded to on his final slide, was that the energy input that's required for these processes. It's a significant energy requirement, but what is the actual quantification of that? That still needs to be done, as well as what are the corresponding environmental impacts and GHG emissions from that energy input into the system. And so that remains an additional challenge that we need to address in better understanding how to make polymers from bitumen. Now, there are others out there, other challenges that you may have thought of listening on the line today. And so if you have those, feel free to share them with us. We're always welcome to hearing additional challenges that we may not have considered in this process. And so with that, I'd like to transition to wrapping up the polymer portion of today's webinar by sharing some insights and conclusions. And so the first one I think that has been imparted on us today in this discussion is that the synthetic polymer industry is very large, it's global, and it continues to grow with the increasing population growth of the world and demand for materials from that increasing population. And so polymers are going nowhere anytime soon in terms of our use and need for them. And so with that, as we make synthetic polymers, that gives rise to environmental and other concerns, such as their ability to be reused and their ability to be recycled. And so those need to be taken into consideration as we go forward into a future with more and more polymers. And so we see that there's a potential now to create new polymers, those that are biologically inspired or demonstrating potential random monomeric ordering, and the processes to make them, may lead to the incorporation of bitumen into these polymers as a feedstock, and allow us to tap into that large potential for bitumen to be used as a feedstock for polymers. And so we really see this as an opportunity going forward, especially with a large and growing polymer demand over the coming years and decade. And so with that, that wraps up the polymer portion of today's webinar. As Carrie mentioned, this is also the final webinar in our 4-webinar series on bitumen beyond combustion. And to wrap it up and to share some insights across all 4 webinars, I'll hand it back to Axel to take us home.
Okay, thank you, Paolo. So here are some closing remarks on our 4-part webinar series. The first really important point to recognize is that rising populations and prosperity drive demands for materials on a very large scale. These are materials that are necessary and desired for housing, vehicles, consumer goods, and you've heard about examples. The second point we would like to make is that producing these materials from bitumen, materials which we call BBC products, but also diversify Canada's oil sands sector with all the attendant benefits that has. The third key point is that BBC products pose a number of very interesting challenges and opportunities. We refer to them as fruitful business, scientific, technical, and environmental and social challenges fruitful in the sense that they are worthwhile, important to work on, and they're very satisfying from the point of view of meeting the needs of the citizens in Canada and around the world, but they're also very satisfying to work on from an intellectual challenge perspective. In these webinars, we have identified 4 major BBC product categories. And by major, we mean products that have the potential of requiring in excess of 100,000 barrels per day of bitumen on a regional and global basis. There are other product categories above and beyond these 4, but let me just recap the 4. The first one relates to carbon fibers and combination products of carbon fibers as they are combined with wood, polymer, and other materials. The second very large opportunity is presented by asphalts, particularly better asphalts. And within asphalts, we discuss the role of asphaltenes as well, which is a primary constituent of asphalts. And a really important challenge is the ability to transport asphalt over long distances without the asphalts remaining molten. And if we can achieve that, then we would have the ability to transport bitumen-based, oil sands bitumen-based asphalts to all parts of the world and meet the needs in Asia and Africa and Latin America in a much more direct way than what we currently experience, where asphalt transportation is by and large regionally confined. Very little asphalt goes offshore North America from the refineries that we have here. The third major category is polymers, and that of course was the subject of today's webinar. And unlike carbon fibers and asphalts, polymers represent a less well explored opportunity if bitumen is the feedstock. There are many more fundamental questions unless one looks at polymer production as an adjunct to typical petroleum refining. But if we want to make special polymers, particularly biodegradable polymers, possibly polymers that are based on proteins as opposed to what we currently make, that opens up very, very different opportunities and presents different challenges. Fourth category relates to vanadium. We didn't run a webinar on vanadium, but vanadium is a constituent in bitumen, and if extracted, it provides an opportunity for large-scale storage of electricity in something that is called redox flow cells. You can learn about all of these polymers and their markets and how to make them in the reports where we give the links on the following slide. So let me conclude then my closing remarks by saying that Alberta Innovates is very interested in BBC, in the products, the making of products. We are supporting in a tangible way the development of products and product technologies. We have invested currently over $2 million in 9 projects to support the development of BBC products. And it is our intention to do more in the future. We will look at larger scale processes. We will look at different products that can be made. And in order to realize the potential that the oil sands bitumen holds for materials, but also in order to meet societal needs in an environmentally and socially responsible way. And with that, I hand it back to Carrie.
Thank you, Axel. Thank you to all of our presenters. Just before we move into Q&As, I just wanted to remind everyone that all of these webinars are available on vimeo.com/COSIA and on stantec.com. Today's webinar will be available within a few days. If you're interested in reading the full reports, the links are here for you to view. Also, if you're interested in getting in contact with any of our presenters, their contact details are listed here as well. So with that, we do have a few questions coming in, so I guess we'll get started here. So first question, what portion of a barrel of bitumen can be used to make polymers? Can we convert all the bottom of the bitumen barrel into polymers?
You want me to answer that? Well, okay, the definition of the bottom of the barrel is somewhat approximate as well, but if by that we mean the bottom maybe 20% by weight, it depends on what kind of polymer we want to make. I think a significant portion of that could be made into polymers, although I would point out that the bottom of the barrel may be better suited to making carbon fibers. And you can actually think about carbon fibers being a polymer, although not the polymer of the kind that we, in the plastic sense, but it is a polymeric material. There is an opportunity to look at the lighter constituents in bitumen than the bottom of the barrel constituents, especially if we want to think about protein-based polymers. So I'm sorry, I can't give you a very specific answer, like 20 or 30%, but it is a significant fraction that would be suitable as a polymer feedstock.
Great, thank you. We heard in an earlier webinar about adhesives and composite or engineered wood. Can bitumen-derived polymer components be targeted to the recycling market of other consumer-sourced plastics? Can bitumen-sourced components become fillers and additives to create recycled plastic materials?
That's a big question. Kerry, would you mind repeating it again?
Sure. So we heard in an earlier webinar about adhesives and composite or engineered wood. Can bitumen-derived polymer components be targeted to the recycling market of other consumer-sourced plastics? That's the first part. Can bitumen-sourced components become fillers and additives to create recycled plastic materials?
I think the short answer is yes, and there's a yes and no component to it. Is it depends on the application, and I think I'll jump to the end question there because it's a little bit more easy, as it were. Meaning from a carbon black perspective, carbon black is typically used as a pigment, and the most common pigment that we encounter is in car tires, vehicle tires, aircraft tires, and so forth. That's a very common pigment. But even within the realm of the carbon black that goes into that application, it is a very sophisticated product. It is not a straight drop-in product. To the first part of the question, could it be used in other areas? No doubt it could. It would require its own independent investigation.
Maybe I could comment on the adhesive part of the question. I think there are likely constituents in bitumen that could become good precursors for adhesives. We haven't really explored it. And on a tonnage basis, that may in fact not approach the 100,000 barrels a day or more than that we have been looking at. But they can represent very high value products. The other way to respond to your question is to go back to asphalts. When we speak about asphalts, we're really speaking about asphalt binders, and it is that binder that causes the adhesion between the aggregates or the granular material. So there is an example of an adhesive, although I think the questioner was probably thinking about adhesives not in the form of asphalts, but it demonstrates that there are constituents in bitumen right now that are in effect being used as adhesives, and the example is asphalts.
Thank you. The next question has 3 parts to it, so take it one at a time. What is the global breakdown of revenues and profits by market segment?
We don't have access to all that information right now, but we had the breakdown of the different polymers on their tonnage basis we provided in the phase 2 report and in this presentation. The profitability of those elements, I suppose that would depend on a number of different parts. Does anybody want to add to that? But what we do know is most of them are still growing, so they must be profitable in that respect.
There are a number of proprietary reports that are produced by different industry and consulting groups. For example, if you wanted to look at the profitability of polyethylene or polystyrene, that is available, but it is but even that is aggregated, and we just presented the overall numbers for the collection of these polymers.
Okay, great. Is 3.9% growth rate realistic given current environmental concerns?
I think it's going to be challenged, and I think we alluded to, and to be honest, the biopolymer element of where this question I think is headed is a presentation series all unto itself. So I think there's more pressure for people to be producing more biopolymers. So going into some specifics, is 50 billion plastic bottles in the US sustainable and a challenge going into the future? I believe so. So I think there's going to be, there are a few initiatives to look at substitutes on a biopolymer biodegradable option. Anybody want to add anything?
Yeah, I'd add to that, Kerry, that it is a very good philosophical question. Whether the 4% is realistic or not, that suggests a mechanism, a feedback loop into the polymer industry, that the polymer industry throttles back, that society throttles back. I don't see that happening. But I do see pressure happening increasingly from an environmental perspective, and we've seen that increasingly happen. I think it was 2017 in December, where China said, we don't want waste recycled plastics being sent to us anymore. That creates a ripple effect up the value chain and causes companies to reconsider what they're doing and become innovative in finding solutions. So I don't see that growth disappearing, but there has to be, and there must be, a ripple effect. If you look at a broader detail of companies active in biopolymers, there are numerous examples across the world. This is not a subject that is quiet. It may be quiet to the public, but within the technical domain, it is a very active area that is receiving attention. And if growth is quieter in one area, it will pick up in another area to maintain what we see from a public perspective, a maintenance of growth, as it were.
Maybe I can add sort of a two-faceted response to that. One of them is to make and focus on polymers that are in fact biodegradable, so they don't present the kind of challenges that we've seen in connection with oceans and rivers. But as Nathan and Ken also said, there are some polymers that you don't want to biodegrade because their functional requirement just doesn't permit that. If you think about sheathing, vapor barriers in houses, you don't want them to disintegrate, at least not while the house is functioning. So the other aspect to that is really the recyclability of polymers. And a lot of work has to be focused on how you recycle polymers. And in part, that depends on being able to separate polymers. Because right now, when we recycle polymers, often you have a whole mixture of polymers in your recycle bin. May that be PVCs, ABSs, polystyrenes, etc. And if you start with that as a source material for a pure polymer, again, that's very challenging. So the recyclability issue becomes very important, and that's partly dependent on being able to separate polymers into their different constituents. If we could get a sharp separation of a polymer mixture and we end up with just pure polyethylene in one stream and pure polypropylene in another stream, that gives you the opportunity for recyclability to a much greater extent than what is currently the case. And there are some interesting technical, scientific, and logistical questions in that respect.
Thank you. How much would pre-treatment of bitumen for feedstock add to current costs?
Question is whether you have to end up with a very pure feed stream or whether you can in fact tolerate a mixed stream. So if you have to end up with a very pure feed stream for your polymer production process, it would in all likelihood be uncompetitive. I mean, certainly uncompetitive for making current synthetic polymers. If you can devise a polymer processing flow sheet that can take a mixed feed stream, that would be different. So as an approximation, I would say that the increase in cost is at probably 2 or 3 times over what is currently expected.
Great. Quantities of polymers are already produced in the Joffre area of Alberta from traditional feedstocks. Is there any interest from those producers to work towards accepting bitumen as a feedstock?
Do you want to?
So certainly the petrochemical sector in the province and the polymer industry is quite important to Alberta, and we are very interested in engaging with our polymer industry in the province, and that is something that Alberta Innovates is currently undertaking as part of the BBC concept and program.
Yeah, and I think our polymer producers in the Joffre area, in fact, are an example of companies that have been very innovative. There was virtually no polymer production in the 1950s, and if you go back to the chart that Nathan showed you, over that period of time, they have built world-scale polymer production processes, and in fact are supplying the world. The question is, will they be able to accept bitumen as a feedstock? That's one question. The other question is, are there other polymers to be made than the ones that are currently being made, where bitumen feedstock is more conducive? And I think that's probably the primary question that deserves looking at, because it opens up different opportunities and has a completely different cost structure.
Great, thank you. I would expect that polymer production facilities are specialized by range of hydrocarbon feedstock, but to what extent?
They are highly specialized. In most cases, well, in many cases, the feedstocks are in fact natural gas liquids. Ethane, propane are typical examples. And in other cases, they are tied in with refinery processes where the refineries have as one of the early steps a cracking step that produces as a byproduct ethylene and other hydrocarbons that are conducive to be separated and then form the feedstocks. There are some dedicated facilities where you use conventional petroleum in order to make polymers, but that's the rare situation. The integrated approach is the typical approach.
Okay, great. Will there be a webinar about vanadium for electric storage?
Under consideration, I think.
We are demand oriented. If you could indicate that you have an interest, we certainly have enough material to run a webinar. We would be pleased to do that. There is also there are 2 projects that Alberta Innovates has supported that relate to vanadium. One being carried out right now that looks at the use of vanadium in redox flow cells. Paolo, do you want to add?
I think you've covered
okay
well, Axel.
Just very briefly on that, vanadium is getting more and more attention. Last year, the U.S. designated vanadium along with 34 minerals as key strategic minerals for the future. So we've seen since we've finished the phase 2 report, a lot of interesting questions around vanadium. So I think as a group, we'll take that away and perhaps look at another webinar around vanadium. It could be something to do.
Good suggestion. The last question we have so far, can carbon-carbon composites be produced from bitumen?
Carbon-carbon constituents, I assume the question is asking indirectly about carbon fiber.
I think so.
And in theory, yes, it can. And there is development work to that effect. And Alberta Innovates, you'd like to comment at all about your studies?
We have several projects currently underway that look at asphaltenes, which are the primary constituent of the bottom of the barrel, as Nathan refers to it. Asphaltenes is a potential feedstock for carbon fibers. The work is done on a bench scale level, and it's actually quite promising. That is to say, you can make raw fibers that have properties of the kind that you're looking for. Whether you can make the same high performance carbon fibers that you can make from polyacrylonitrile, for example, the kind of fibers, carbon fibers that you find in aircraft components and skateboards and skis and golf clubs remains to be seen. But there are many applications where these very high performance carbon fibers are in fact not necessary. They're desirable but not necessary. And in our second webinar, we explored that a little bit. Good example of that would be the addition of carbon fibers to concrete and carbon fibers to wood products.
Very good example.
Great. Well, with that, if we don't have any other questions, we will close off our webinar. Thank you everyone for joining. Have a great afternoon.
Right.
Thank you.
Okay.
Thank you all.
Thank you.
Thank you, Kerry.